Here's your explainer video for AP Physics 1, Unit 1.4, assignment on free fall. Question 1, you have two small metal balls. You drop the first one and throw the other one in a downward direction. Choose the statements that are not correct. So again, just to be clear here, the first one is just dropped, so its initial velocity is 0, and the second one starts with an initial velocity of something. The second ball will spend less time in flight. That's true. It's going to hit the ground faster. The first ball will have a slower final speed when it hits the ground. That's also true if it's dropped versus thrown downward. The second ball will have a larger acceleration. That is not true. Both will have an acceleration of negative 9.81 meters per second squared once they leave your hand. So once they are just projectiles, once they are free to, well, that didn't work. Once they're free to fall, so once it's left your hand, again, the acceleration will be negative 9.81 meters per second squared. So both balls will have the same acceleration. So the correct answer to which is not correct is choice C. Question 2. Jason hits a volleyball so that it moves with an initial velocity of 6 meters per second straight upward. Calculate the displacement of the volleyball 1 second after he hits it. I'm going to make a little sketch here. There's the ball. We know the initial speed is 6.0 meters per second. I'm going to assign up to be positive and down to be negative. The amount of time that passes here is 1 second. We know that the acceleration is negative 9.81 meters per second squared, and we're supposed to find the displacement. What I'm going to do before I proceed any farther is I'm going to add a page here, and I'm going to write down my kinematic equations. And I'm also going to think about which variables are included in each equation and which is not included. So delta x equals 1/2 v naught plus v times delta t. This equation does not have acceleration in it. The next equation is delta x equals v naught delta t plus 1/2 a delta t squared. This equation does not have final velocity in it. Final velocity equals initial velocity plus acceleration times time. This equation does not have displacement in it. Final velocity squared equals initial velocity squared plus 2a delta x. This equation does not have time in it. If I go back up to question 1, I see that I've got initial velocity, time, acceleration, and delta x. And if I go back to my choices, this is the equation that has those same 4 variables. So I'm going to use that. I'm going to write it down. So delta x equals v naught delta t plus 1/2 a delta t squared. So I plug in 6 meters per second, plug in 1 second, 1/2 times negative 9.81, plug in 1 second squared. Enter this into my calculator, and I get 1.1 meters as the displacement. Calculate the velocity of the volleyball 1 second after Jason hit it. So now I'm looking for final velocity. Now I have all 4 other equations, or all 4 other variables here. I've got initial velocity, I've got time, I've got acceleration, and I've got I just solved for delta x. So I actually have a couple of things to choose from. There's a couple of right equations to choose from. But what I like to do is pick the one that'll get me there the shortest, simplest way. I'm looking for final velocity, and this equation doesn't have any squareds or square roots in it or anything like that, so I'm going to use this one. So we've got that v, final velocity equals initial velocity plus acceleration times time. Initial velocity was 6, acceleration is negative 9.81, and time is 1. And when I calculate that in my calculator, I get negative 3.8 meters per second. Moving right along. Stephanie sets a volleyball from a height of 2 meters and gives it an initial velocity of 5 meters straight up. How high will it go? Okay, so I'm going to make a sketch here. Here's the ground. It starts 2 meters off the ground. Here's the ball. The ball's going to go up. Eventually it's going to come down, but for right now, what I'm interested in is this portion where the ball is just going up to the top. Now, at the top of its path, the velocity, the final velocity at the very tippy top is 0 meters per second. Its initial speed, or initial velocity, was 5 meters per second. And this thing is a projectile, so I know that the acceleration, again, is negative 9.81 meters per second squared. I want to know how high will it go. So I am looking for delta x above its initial starting height of 2 meters. So it's a little confusing because we've actually got two measurements of height here, but one is the starting height and one is how much higher it will go. So I've got final velocity, initial velocity, acceleration, and time. If I go back to my equations, where I've got final velocity, initial velocity, acceleration, and time, I'm going to use that last equation there. I'll go back here and write it down. And then I'll plug in what I have. So final velocity is 0, initial velocity is 5, acceleration is negative 9.81, and that's delta x. Now when I solve this one, 0 equals 25 plus negative 19.62 delta x. So I would add 19.62 delta x to both sides. And I end up with 19.62 delta x equals 25. And then I'm going to divide. And when I divide, I'm going to get 3.2. Actually, it's 1.28 meters. Sorry, my delta x is 1.28 meters above the initial. So that's a total of 3.28 meters if I start with her initial height of 2 meters, or the ball's initial height of 2 meters. So again, this little yellow bit is 1.28, and then I'd add that to the initial height. How long will it take the ball to reach its maximum height? All right, so I've got the same knowns here. I've got final velocity, acceleration, initial velocity, and I'd like to know now what's delta t, how long will it take? If I go consult my notes, I see that I can use this equation, final velocity equals initial velocity plus acceleration times time. So I've got 0 equals 5 plus negative 9.81 delta t. And when I solve that, I get that delta t is 0.51 seconds. Okay, number 4. A tennis ball is thrown vertically upward with an initial velocity of 8 meters per second. What will its speed be when it returns to its starting point? So we looked at this, we looked at a problem like this in class, and I think I'm going to replicate it real quick here. So let's say that I have a ball that leaves my hand with an initial velocity of 30 meters per second. And for the sake of this example, let's say that the acceleration is negative 9.81 meters per second squared, which I'm going to round to 10 just to keep the math easy so we can focus on the concept and not the calculations. Now, an acceleration of negative 10 meters per second squared is the same thing as negative 10 meters per second per second. In other words, the ball's speed decreases by 10 meters per second every second. So at t equals 0 seconds, again, let's say the ball leaves my hand with an upward velocity of 30 meters per second. 1 second later, I would subtract 10 meters per second. So 1 second later, the ball would be going 20 meters per second because it's because of this. The ball speed decreases by 10 meters per second every second. Another second later, the velocity is 10 meters per second. And approximately 3 seconds later, approximately 3 seconds later, the velocity of the ball is 0. Now, what happens next? The ball starts to come down. I'll do this in a different color. So at 4 seconds now, the ball is going down with a velocity of negative 10 meters per second. And another second later, the ball is traveling at negative 20 meters per second. And finally, at 6 seconds, the ball is traveling at negative 30 meters per second. So I show you this to show the symmetry of what's going on. The symmetry. And the symmetry is true when we're looking at the ball at the same height in the air. So let's go back to this question now with what we now know. What will its speed be when it returns to its starting point? Well, it's going to be the same as what its launch speed was, so it's simply going to be 8 meters per second. How long will it take for it to reach its starting point? The initial speed of the ball was 8 meters per second. If it goes up and comes down to its initial spot, its final velocity would be negative 8 meters per second. Its acceleration is negative 9.81 meters per second squared, and we'd be looking for delta t. So I'm going to use the equation I used in 3b. Final velocity equals initial velocity plus acceleration times time. And negative 8 equals 8 plus negative 9.81 times time. I'm going to subtract 8 from both sides, so I get negative 16 equals negative 9.81 t. And I'm going to divide both sides by negative 9.81. And when I do that, I get that delta t is 1.63 seconds. Okay, number 5. A flower pot falls from a windowsill 5 meters above the sidewalk. How fast is the flower pot moving when it strikes the ground? So here we've got a displacement, 5 meters. It falls, so I'm going to assume that the initial velocity is 0 meters per second. It's a projectile, so the acceleration is negative 9.81 meters per second squared, and I want to know its final velocity. The equation that we're going to use, and we haven't used this one yet. Oh, yes, we have. We're going to use the circled yellow one. Final velocity, initial velocity, acceleration, and time. So let's go back. And final velocity squared equals initial velocity squared plus 2a delta x. So oh, I messed something up here. So the flower pot, the flower pot is falling. So delta x is actually negative. So I should have put a negative 5 here. If I didn't do that, I wouldn't be able to take a square root and get a rational number. So that was important. When I solve this, I get that the velocity is 9.9 meters per second. Part B, how much time does a passerby on the sidewalk have to move out of the way before the flower pot hits the ground? So now we're looking for delta t. Again, I like to use the simplest equation I can. I have final and initial velocity, so let's use this one. 9.9, 0, negative 9.81, delta t. And when we solve that, get that delta t is 1.01 seconds. All right, I'm going to pause here and I'm going to render this video, and I will come back with a new video for the second page.